Hello everyone, welcome back to Advent of Code Day 10. Today's problem is called factory and it goes as follows. Just across the hall you find a large factory. Fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by a Shiba Inu. All that remains of the manual are some indicator light diagrams, button wiring schematics, and voltage requirements for each machine. For example, so this is how our input would look like. This is our light diagram. This is the wiring for each one of the lights from 0 indexed. So this would correspond to the light on a index 3, light on index 1, light index 3, and so on and so on. And these are the voltages for each machine. The manual describes one machine per line. Each line contains a single indicator light diagram in square brackets, one or more button wiring schematics in parentheses, and voltage requirements in curly braces. To start a machine, its indicator lights must match those shown in the diagram, where dot means off and hashtag means on. The machine has the number of indicator lights shown, but its indicator lights are all initially off. So, an indicator light diagram like dot hash hash dot means that the machine has 4 indicator lights which are initially off, and that the goal is to simultaneously configure the first light to be off, the second light to be on, the third to be on, and the fourth to be off. You can toggle the state of indicator lights by pushing any of the listed buttons. Each button lists which indicator light it toggles, where 0 means the first light, 1 means the second, and so on. When you push a button, each listed indicator light either turns on if it was off or turns off if it was on. You have to push each button an integer number of times. There's no such thing as a half press, nor can you push a button a negative number of times. So a button wiring schematic like 034 means that each time you push that button, the first, fourth, and fifth indicator lights would all toggle between on and off. If the indicator lights were hash dot 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 dot, pushing the button would change them to be dot 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 hash hash dot. So you can push each button as many times as you like. However, to save on time, you will need to determine the fewest total presses required to correctly configure all the indicator lights for all machines in your list. There are a few ways to correctly configure the first machine. For example, we will be using this as our input. You could press the first 3 buttons once each, a total of 3 presses. You could press buttons 1, 3 once, button 2, 3 once, and button 0, 1 twice, a total of 4 button presses. You could press all of the buttons except button 1, 3 once, and which would equal to total of 5 button presses. However, the fewest button presses required is 2. One way to do this is by pressing the last 2 buttons, 0, 2 and 0, 1 once each, and so on and so on. Analyze each machine's indicator light diagram and button wiring schematics. What is the fewest button presses required to correctly configure the indicator lights on all of the machines? So part 1 is a simple breadth first search problem, or say sort of a pathfinding problem, where we will try to get a minimum amount of steps, or in this case a minimum amount of button presses that we need to reach our target. So first of all, as always, we will start with parsing our input, which in this case looks like this. It isn't simple to just parse it normally, but we have some tricks up our sleeves. So I will create a normalized input variable that will be a list, and where we will be storing all of our inputs, where lines that we are parsing as f. Then we will start with for line in f, we will split our line by the space. So we will now we will also strip it of any new line characters. We will split. Oh, just a split, not necessarily anything more than that. And now to get our target light diagram, so how this would look like, actually I can do print of split line. And now we would get something like this. This is our first line. And our first element is gonna be, sorry, our first element is gonna be our light diagram target. So, and our last element is gonna be our voltages, and everything in between is gonna be the, how do we call them, buttons. So let me just delete this. And now we can do target light, how is it, diagram, yeah, diagram. We will turn it into a list since it was a string initially. And what we will do is we will go through the light diagram and we will turn it into a Boolean list. So basically false if it is a dot, true if it is a hash. So what you can do is light equals a hash for light in split lines of our first element, and we want to get rid of the square brackets so we can get it from the first element up until the last without including the last one. For the buttons, for our buttons, we can basically do the same, but this will be a list of lists where basically we will convert each button into its own list, because it will be, for us it's easier to work that way. It will be each individual coordinate. So we can just do this and go list, and we will map button values to each one of the two integers, all of these button coordinates to integers. And we can do button. We again do this so we can get rid of the parentheses in this case, and we will split it by the comma. List, is that good? Yeah, for button in split line, and we of course now ignore first and last element in our list, and then we can do voltage. Voltage is gonna also be a list, a map of integers. We will do split line of a last element, and we will again get rid of the, in this case, curly brackets, and we will split it by comma, since here we have commas. Now once we have that, we can store it into normalized input as a tuple. It's just a preference, honestly. Buttons and a voltage. Now once we have that, we can start writing our DFS, not DFS, in this case, breadth first search function, def BFS, which will accept our target light diagram and our buttons. So how does DFS, oh my god, BFS work? So let's imagine we have a graph of nodes. Actually, I can show it visually. To quickly explain how breadth first search works, we will be keeping a track of two things. We will have a visited and to be visited nodes. Our starting node will be a node A, and of course we will be storing all of our nodes in a queue. So let's begin. So to be visited, we'll be marking letter A like this for now. I'm sorry for that. Now, once we have letter A, E to be as a thing to be visited, we can also have our Q, which is gonna be, which will have that A inside of it. Let me just maybe, actually not, doesn't matter. And now we are visiting this node, so we pop the letter A from our queue, and now we can freely mark it as a visited node. Then what we do is we store inside the queue its direct neighbors, that the neighbors that the node A is connected to. In this case, it's B and C. So we store like this. And now, to be visited, we can mark again, sorry, I'm just gonna copy this one because it's gonna be simpler. Now this and these ones are gonna be to be visited. Now we pop again the first item from our queue, which in this case is gonna be B. We can define this as a green. And then again, we do the same thing with D and E, where we mark them as nodes to be visited. Why is it not? Okay, to be visited. And now in here we have E, D, and C. And then we go so on and so on. And we are doing that until our queue is empty, or in this case, for our current task, for today's task, until we reach a target light sequence. So let's continue writing our breadth first search algorithm. I will import a queue from collections. Not queue in Python is the queue. This will be our queue that will be keeping track of our current nodes that we need to be visiting. We will define our target as a tuple of target light diagram, and we will get our length of our target, which is going to be a length of the target. Should it be in the length? No, I guess it doesn't matter in this case, but we can do this. And we will start, and our first node will be our current diagram. It will be defined by current diagram. In this case, we will initialize it all to be off. So we'll do false for nothing in range of our length of target. So this is now gonna be equal to, for example, for this first line where we have 4 elements, 4 lights, it will be false, 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 false. And we will mark a visited. Visited will be holding our visited nodes that we have checked. And here we can start with a current diagram. It will be a dictionary, and it will hold a current diagram, and it will have a values of 0. So this will be our current diagram. The key will be the this light sequence, and this will be how many times we have pressed on that current sequence. Let's define a queue, dq, and we will add in here our current diagram. And while queue isn't empty, or in this case while queue, we get our first element. I forgot to mention that that breadth first search also works on a principle of so-called FIFO, first in, first out. And now we get how many. We will just name this variable how many times. We will get a visited of our current diagram, and we will add 1 to it, so we know that we are visiting it at least for the first time once. We increment it basically. And now we go through each started writing wiring through each buttons. For buttons, we will get our next current, which is now gonna be the following. We will also define a tuple from it. And now we remember from the task where it said that if a light is on, when there is a button that also presses that light, it goes off, and if it was off, it goes on. So that's what we will now do. So we'll do not current diagram of I, if I in wiring. Oh my god, why wiring? Just keep thinking from reading the task. Button, else current diagram. Yeah, else current diagram of I for I in range where we have a length of our target. And now we have our next current target that we'll be checking. So now we can do what we check if our next current is not in visited. Not in visited. Whoa, not in visited. But if it equals to our target, we just return how many times. Otherwise, we add the next current diagram to our visited, and we append it to our queue. Next current. And once we have that, we will also do a fallback, return 0 if none of it is found. And what we will now do, I guess we can name a variable fewest presses light sum. Yes, fewest presses light sum, and we will now just sum all of those lines together. We will do a BFS of the target and buttons for target, comma buttons, comma nothing in normalized input. And that should be it. And we can now just print our part 1, fewest presses light sum. We get 7, which is the correct answer for the example input. And now let's run on my input. And this is the correct answer, 512. Let's begin with part 2. I'm not gonna be reading through it because it's practically the same. Again, it's not the same, but but now instead of the light diagram, we need to reach a voltage target. So basically this 3, 5, 4, 7 means how many, what's the voltage needed for each light, for each light to work, for the machines to function properly. So we will again be using our buttons that we have currently, but we will also be tracking how many times they have been pressed. What that means is we start from each button presses as 0. In this case, we have 4 lights, so we will have 0, 0, 0, 0. And with our example input, if you press a button with coordinate 3, we will then have 0, 0, 1, 0. If you press 1, 3, it will be 0, 1, 0, 2, since we already had this button pressed, and so on and so on. For this, we'll be using a library called Z3, because besides it, or without it in this case, I am not sure how we would solve this. But this is basically a system of linear equations that we need to solve. They're all of variable length and whatnot, so that's what makes it even more complicated. So I prepared here our buttons marked all individually with their variable names. And here we have our target, here we have our voltage targets for each individual light that we will be using. So how this would work? So let's say, for example, we have a target index, and we will start with that index of 0. As we'll be going through our targets, target light values, voltages, we'll be using. So we can start, of course, with I equals 0, which is then gonna be, I guess I can create an arrow. That's the wrong side. Let me just create it like this quickly. Gonna give it a red color and gonna make it bit thicker. Okay, so now once we have that, our target index is 0, so we're trying to find buttons that have a target index of 0 in our button list. So this first one doesn't, second one also doesn't, third one no, fourth one no, but the fifth button has 0 and 2. So we know that is gonna be our first variable that we can use to construct our, how do we call it? To construct our number 3. And we also have this 0, 1 button number 6, which also contains a 0 index, which will then also be which will be x4 plus x5 now. Since we don't have any more buttons which have the 0 index, we can just do it like this. Now we continue with our target index being 1. Target index being 1, and this arrow sort of moves. We now continue. So we're searching which one has 1. Aha, okay, so we have x1 plus this one doesn't, this one doesn't, this one doesn't, this one doesn't. Oh, this one does, my bad. We do plus 5 equals to 5. Then we move this gets to 2. Now we're searching each one that has 2. No, no, x2 plus x3 plus x4 equals to 4. And finally, we have done this. We then have that. And now we're searching which ones have 3. So we see x0 plus x1 plus x3 equals 7. So that is going to be our system of linear equations. I hope I don't have to say how complex this would be inside to do in a code. If someone can do that, then kudos to them. I sadly can't, and I wouldn't even know how to begin. So we'll be using a so-called Z3 solver. Z3 solver that will help us with that. So what Z3 solver basically is, it's a SMT solver, and SMT stands for, I have it here, Satisfiability Modulo Theories Solver. It basically helps us with use cases like this, so we don't have to do them ourselves. We are basically creating sort of equations where then Z3 solves them or tries to prove them. At least to my understanding, that's how it works. So let's start with solving our part 2. What we will immediately do is from Z3, we will import a couple of necessary functions. One of them will be optimize. This is basically a method, not a function, that allows us to initialize our solver. We will import int, sum, and set. Int is here used to create variables of a given name, of some name. So basically, for example, we can have variable int x and then we can do something on top of that. Sum basically creates the sum of Z3 expressions, and SAT is basically checks if a equation is satisfiable or if we can get a result from the Z3 equation we have created. So I'll start writing the function below here, and we will call it get mean button presses for target voltage. A mouthful, but at least people will know what it is used for. And we will pass it buttons and our voltage. So now once we have written our function, we can slowly start initializing our Z3 solver. We will create a variable called optimizer, which we'll call the optimize method. And we will keep create a new variable called press count, which will keep a track of how many times we have pressed a button. To create our variables for each specific buttons, we will do for I in range length of those buttons. This will basically be like those x0, x1 that we have shown in an example. We'll create a variable and it will be integer, and here we can just do like a button of I. So instead of being x0, x1, we just have like b0, b1, b2, and so on and so on. We will add it to our optimizer. And one important constraint we need to make is make sure that this cannot be negative, because we cannot press a button negative amount of times, like -1 or -2. And we will add the variable to our press count. We will now get our target length, so we can use it for later on, which is going to be length of voltage. And now comes the most important part, where we will actually start setting up our checking with our target index and whatnot to build to check which buttons contribute to our buttons, to our lights. So we will create a contributors array. It's gonna be an empty array, and we will go again through each one of the buttons. Button for in enumerate buttons. And now what we will check is the following. If we have our target, if our index of the target length is inside one of the buttons, so this is basically the target we had, like I don't know, let's say we had a target 1 and the button had like 1, 3. So 1, in this case J, is inside of a button, so we can do something with it. If our J is in our button, we can append it to our contributors by getting from press count our variable of a button that we have created, press count of I. Now once we have that, what we can do also is, now we need to add it to our, we add the contributors to our optimizer. So if we have contributors, we add them to our optimizer, optimizer.add, and we will add a sum of those contributors, voltage of J. So now we have added our equation, and we have just told it, hey, for this position, for position J in our voltage, which is basically like a light at that specific spot, should be equal to the sum of all of these previously defined buttons. So how many presses it actually takes. It's basically the x0 plus x1 which we had, which would equal to, I don't know, 3 for example. Else, if we don't have our contributors, we will just check if our voltage of J is bigger than 0. If it's bigger than 0, we'll return 0. What we just did with this is to check if like if no button touches the current index that we are on, basically it's impossible state to get. And now what we can do is do a total presses, which will be equal to the sum of our press counts. And through our optimizer, we will try to find the smallest possible, to get the smallest possible value from all of our equations. In this case, the smallest possible amount of total presses that we need. And now what we do is we check. Optimizer has this check method, which checks the given expressions which calculates the given expressions. Basically, it's the heavy lifting part of Z3 solver. And we have then this SAT, which just checks if the expression is satisfiable. If it is, we then run for the not optimizer.model. Yeah, optimizer.model. We now get a model of our optimizer, which basically then calculates the sum of the numbers that satisfy all of these constraints that we have defined. And what we can just do is return a model.eval of our total presses as long. Basically it turns it as a big int. Else, if there is nothing, we return 0. I guess I can copy paste the same line, but fewest presses light sum, not light voltage. This can be like that too, voltage sum. And instead of writing a here BFS, we do this, and we don't have target buttons anymore. We remove this and voltage in normalized input. Do that. Okay, that should be it. Let's run it on our example. 33, that is the correct answer for the example input. And now let's see on mine, which is 90,857, which is the correct answer. So that was it. The problem, the part 1 was pretty simple. It was just a standard Bradford search. But the second part was, if we would go do it without using some solver like this, I think it would be extremely difficult. But using Z3 solver is just a matter of creating the system of linear equations, and that's it. So I wouldn't classify this day as harder than the yesterdays, at least for me. But yeah, that's it. I hope you guys have enjoyed and have learned something. And until tomorrow, I hope you enjoy your days, and peace.